In today's video, we get to expand our repertoire of functions that we know how to work with. Up to this point, we've really only worked with power functions, right? Where you have your variable raised to some power. Every function we've looked at so far can really be boiled down into a power function. Polynomials? Polynomials are just sums and differences of power functions with coefficients in front. Linear functions? Linear functions are just polynomials. Root functions. Remember, roots we can rewrite with fraction exponents, and so they become power functions as well. But today we're going to introduce a fundamentally different equation, or a fundamentally different function called an exponential function. Okay, exponential functions look something like this: a naught times a to the x, where a naught represents your starting value. We can also think about this as my y-intercept. Right? What's your value when x is 0? We call a the base. And then x, of course, is usually either just my variable or some function that has my variable in it. Okay? And that's the big difference between a exponential function and a power function, is where the variable is. In an exponential function, the variable is in the exponent. In a power function, the variable is being raised to some exponent. Okay? And that's what makes these fundamentally different. One of the biggest mistakes I see in this class is, now that we've introduced exponential functions, students want to just use the power rule to take the derivative of an exponential function when they're not the same. They're not the same. Okay, so what makes a function exponential? Exponential functions come from repeated multiplication. We've seen something like this before with linear functions. Linear functions, because you have a constant rate of change, linear functions represent repeated addition. You're always adding that, whatever your slope is, you're adding that amount over and over again. Well, exponential functions are similar in that you're always multiplying by the same value. And that value that you're multiplying by is whatever your base is. Okay? I'm multiplying by a repeatedly. And repeated multiplication turns into exponents. For that reason, we actually have some ground rules for my base. Okay? If I multiply by a negative value over and over again, your sign is going to constantly switch. And so we always say that a must be greater than or equal to 0. Okay? But I'm actually going to go one step beyond this. What would be true if your a was 0? Then I would be multiplying by 0 over and over again, which, what does that give me? It just gives me 0. It's just the constant function of 0, which is not special at all. I have simpler ways to write that. So for that reason, we're actually going to say that a has to be strictly greater than 0. And there's actually one other number that we're going to disqualify, and that's a equals 1. What happens if you multiply by 1 over and over again? Your number stays exactly the same. So we're also going to say that a cannot equal 1. Okay, so with that in mind, let's get into the different types of exponential functions. Okay, there are two big varieties of exponential functions: exponential growth and exponential decay. Okay. If I were to graph a growth function, we would see it start at your starting value, a naught, and slowly curve up from there. How fast you curve depends on what you're multiplying by each time. It depends on what a is. Okay? Because whatever your a naught is, your next term at 1 will be a times whatever a naught was. And then your next term at 2 will be a naught times a twice. Right? I'm multiplying by a over and over again to get my future terms. Okay. On the other side, my graph actually flattens out to 0. And the reason why is because if I go into negative x values, instead of repeatedly multiplying, I'm repeatedly dividing. And when you divide, your number just gets closer and closer to 0. Well, with decay, I'm just going to switch it. I'm still starting at my starting value, but my function flattens out to 0 on the right side and goes off to infinity on the left side. So that's how their graphs differ. So before we get into what makes something growth and what makes something decay, let's look at some common characteristics here. For any exponential function, notice what the domain is. I can plug in any x value I want. My domain is negative infinity to infinity. But I do have limited y values. What's true about my y values? My y values are always positive. So my range goes from 0 to infinity. Okay. I always have a y-intercept. As long as I'm not doing any horizontal shifts, I always have a y-intercept at a naught, your starting value. And then same thing, as long as I don't have any vertical shifts, there's always an asymptote at y equals 0. I always have a horizontal asymptote, specifically horizontal asymptote at y equals 0. The graph will never cross the x-axis. But what makes something growth and what makes something decay? Well, it all depends on what I'm multiplying by over and over again. So if I think about growth, what would I need to multiply by in order for my number to get bigger? Well, it turns out you just need to multiply by a number greater than 1. So as long as your base is greater than 1, you're going to have a growth function. Okay? Well, what about decay? If I want to multiply by a number and end up with a value smaller than what I started with, I need to multiply by a number smaller than 1. Right? If you have the number 5 and you multiply 5 by 1/2, your number gets smaller. You end up with 2.5. I will say, though, that decay is also very commonly written in a slightly different way. So you can also see decay written like this, where a is actually bigger than 1 and the exponent is negative. Okay, for example, you might have something like 5 times 2 to the negative x. 2 is greater than 1, so if I ignored the negative in the exponent, I might think this is growth. But that negative exponent means I'm going to flip it across the y-axis. It means when I try and plug in 4, I get 2 to the negative 4th, which of course gives me a fraction. Okay, so this is just an example here. Okay, so that's just the basics of what an exponential functions are. And the reason why we like exponential functions is exponential functions are really useful in a lot of applications, like population growth. Anything where the previous value affects the rate of change, right? And something builds on itself. So because of that, exponential functions, we see them a lot in real life applications. But what about their derivatives? Okay. Before I move on to that, go ahead and pause the video and you can try a few of the problems of just graphing exponential functions. You can try them out. But then we're going to move on to how do I find the derivative of an exponential function? Okay, I forgot to mention, I would be remiss if I didn't mention another big example of where exponential functions come into play is interest, right? If you have an account with money in it, that interest is exponential growth, because the more money you have, the more you're going to make. Anyway, so let's talk about derivatives. How do I find the derivative of an exponential function? Well, according to the constant multiple rule, that a naught, that starting value, doesn't actually affect my derivative at all. So I can just focus on what's the derivative of a to the x. Well, let's try this out. Let's try this out by using my limit definition of a derivative. So I'm going to use my difference quotient. I get a to the x plus h minus a to the x over h. Using some exponential properties, I can see that this is a to the x times a to the h minus a to the x. And now both of my terms in my numerator both have an a to the x in it. So I can pull that out. And I get a to the x times a to the h minus 1 over h. Since a to the x doesn't depend on h at all, I can actually pull that out. Well, what does this tell me? This tells me that my derivative is equal to a to the x times this limit as h approaches 0 of a to the h minus 1 over h. Well, notice this piece right here doesn't involve x at all. It's completely in terms of h. So I guess there's a chance that this h might not exist, or sorry, this limit. There's a chance that this limit might not exist, but if it does exist, I'm just going to get out a constant value. So what they were able to figure out was that the derivative of a to the x is just some constant multiple of itself. I get some constant times a to the x, where that constant is equal to this limit that we came up with, a to the h minus 1 over h, as h approaches 0. Well, when mathematicians first noticed this kind of begged the question of, well, can I pick a specific base such that this constant ends up being equal? So can I choose a such that the limit as h approaches 0 of a to the h minus 1 over h is equal to 1? Well, it turns out you can. It ends up being the irrational number e. Hopefully you guys have seen e before in some of your previous math classes. E is known as Euler's number. Okay, actually I should have written that lower because E is approximately, I'll write this right here, E is approximately 2.718 ... It's irrational, which means that decimal goes on forever and never repeats. But this is called Euler's number. And this E value has the very special property that when you take the derivative, you end up with a constant times e to the x, but that constant is just 1. So this gives me a great place to start. Your derivative of e to the x, so if my base is this very specific value e, if I choose my base to be e, Euler's number, then your derivative is just itself. The derivative remains exactly the same. Okay, but that still doesn't answer my question. That answers my question for a very specific choice of a. But based off of knowing that e is that special number where the derivative is just itself, we can actually find what the derivative of a to the x is. Derivative of x is, like we said, is just some constant times a of x, but it turns out that constant is the natural log of a. Times a to the x. Okay. Now, some of you guys may have seen that natural log notation might seem familiar to you. You guys remember talking about logarithms in previous classes. We are going to talk about logarithms later in this section of what they are, where they come from. But you can find that natural log function on your calculator for when you're finding these derivatives. Okay. Well, a lot of times when we're working with exponential functions, instead of seeing it just as a to the x or e to the x, most of the time we see our functions with some constant being multiplied by my variable. Okay? Most of the time, this is how we see exponential functions. Base raised to a constant times x. So how does this affect my derivative? Well, this derivative, since I know how to do the chain rule now, I can use the chain rule to find this derivative, right? I'm going to take the derivative of my outside function, which of course is just itself, keep the inside function the same, but then I'm going to multiply by the derivative of my inside function, which is just k. Similarly, if I did this with an exponential function that just had with any base, I get natural log of a times a to the kx times k. Okay. We often rewrite that as k e to the kx, and this as k natural log of a to the, I'm running out of room, a to the kx. So these are my nice derivative rules for exponential functions. Okay. And let me rewrite these to make it look a little bit nicer. So feel free to pause the video and go back and start working on some of the derivative problems in this chapter. But after this, we're going to go through one or two examples. Okay, so now let's take a look at this example. I have f of x is equal to e to the 5x over x to the 15th power. If I want to take the derivative, what am I going to use? Quotient rule. Okay. But I chose this one because these are two fundamentally different functions. The top function and the bottom function are fundamentally different because my top function, once again, is an exponential function. So my derivative of my top function would be 5e to the 5x, right? Your function stays exactly the same, except I'm going to multiply by whatever constant is up there with the exponent. But g is a power function, and so I use the power rule, 15x to the 14th power. Bring the exponent down and then subtract 1 from the exponent. Okay, put these together. And you get x to the 15th times 5e to the 5x minus 15x to the 14th e to the 5x all over x to the 15th squared. I can, of course, simplify this, but we're not going to bother. Okay, because on your homework, you won't have to simplify. Okay. What about something like this? Okay. First off, can you tell me, is this a growth function or demand function? It looks like there's a lot going on, but this is just a basic exponential function. Here's your a naught, E is your base. I do have a constant up there with my x, but it's still exponential. What is this growth or decay? Well, this is a good example of something that's decay, even though my a value, my base value is greater than 1. E is greater than 1. It's 2.7 something. But because I have a negative up there in the exponent, it's actually a decay function. So what would my derivative be here? Once again, 170, that's just a constant being multiplied by in front. So I can just leave the 170 there and then use my derivative rule for exponents. I'm going to multiply by my constant that's up there, negative 0.005, and then leave everything the same past that. And then, of course, I can simplify by multiplying 170 times negative 0.005. Okay? Okay, good luck on your homework. Let me know if you have any questions.